This week we are continuing with the understanding of implementation aspects, and we are into the third major implementation aspect that we are looking at. We introduced you to the ion trap scheme, which has been one of the very important and successful approaches of quantum computing. In terms of the approaches that we have discussed before this, the major aspects were in terms of NMR. Then we came and talked about optical schemes, and then we also mentioned that optical schemes have been utilized in conjunction with many other approaches. So, we went up to a certain level and then left it, and then we entered one of the other major advantages or applications of quantum computing implementation has been, which is the ion trap case. And in this particular ion trap case, the advantages has been that it represents the simplest form of qubit representation, which is the atom itself to start with, or its corollary, which is the ion that we are looking at. So, we discussed how typically this has been utilized in many different ways. In this lecture, now on, we basically look into the various different aspects of ion traps which have been utilized and how it stands in at present time in terms of its implementation as well as its advantages into the future. So, with this, let us look back into our ion trap issue. So, we basically know that the trapped ions are generated inside a setup where we have these RF being applied with oscillatory fields, so that the trapping condition is achieved, and we are able to put multiple ions in relation to each other, so that their independent states, which basically represents the internal property of the system as well as the proximity. So, basically there were two different aspects that we looked at. One is the principle of the individual internal state of the ion that we are talking about, and secondly is the relative position of a bunch of ions that we are looking at. So, that is how we have been discussing this issue of the ion trap and how it has been taken advantage of. So, in some sense it is say the state of the ion that we are looking at, that is the internal state, whether it is in the ground state or excited state. Then the second one is the polarization, very often that is also sometimes which are used, polarization of the ion state. And the third one, which is often used, is the position or the relative motion of that. So, that is translational. So, it is sort of related to the momentum. So, or energy in that sense also. So, basically many a times these two are coupled in order to get advantage of multiple quantum bits being encoded at the same ionic conditions. So, this is how the gates and the ions in the ion trap have been utilized, and roughly speaking we showed how the addressability of these ions can be achieved by using lasers, which can then be modulated to be off and on, and that additional to the condition of the ion which is being placed with respect to its property as well as its relative position can all be put together into use when we look at the implementation of quantum information or other aspects of quantum into the ion trap condition. So, with that background, now we also discuss some of the major candidates for these ion states, and they are mostly candidates like calcium, strontium, barium, mercury, each of them singly ionized, so that we have one electron available in the outermost state, which could be then utilized as available entity which could also be used. And so, these are states which are long lived, and so that is why we have the advantage of keeping them for a very long period of time. We also looked at it that under conditions where we keep it at we can actually isolate it to a very good extent, then the lifetimes can be extremely long, and so that has an advantage in many of these operations. So, one of the principles which have an advantage in this ion trap case is the long lived electronic states that we are looking at. Also, there are many of them which have hyperfine ground state levels, which are very long lived, and that is another place where the addressability of these states have been achieved by using say RF or megahertz or gigahertz pulses, which can radiation which can then address these states, and these states are say stable to for example, in this case for some of these ions that we show in the range of over 10,000 years in terms of the stability of the state that you are going to create with respect to the starting state. So, that is the long livedness of these states are extremely advantageous when you are looking at the implementation aspects in terms of quantum processing, as we have been discussing. So, one of the examples which were utilized and used was the C naught gate, as for example, on beryllium ion in the ion trap, and this was one of the example where after the control knot what happened, before the control knot gate application what happened, and we are coming to this in a minute. So, this sort of like shows that these traps have been utilized. So, the other property which we were discussing at the very beginning is the mode of the ion oscillation. So, there can be the lower energy phonon mode, which is due to the relative positioning of these ions with respect to each other. When they are further apart, then it is the lower energy phonon mode. When they are closer to each other, then it becomes a higher energy phonon mode, and so that is how you can get these other coupled states, which can then it can become a 2 qubit condition instead of the single qubit, which is due to the internal energy state of the ion per se. So, the interaction which is between the ions, which is the phononic interaction, for instance, in this case due to their motion, ion oscillation is one kind of mode, and that can be addressed in addition to the internal state of the system. So, for example, here is the energy level of a single ion spin phonon. So, here we are talking about spin as well as the phonon coupling conditions, and the phonon the spin of the ion is thereby connected to the phonon state because of the oscillations which are due to relative motion versus the spin condition of individual ions, which can be kept at of one kind versus the other, and that can be addressed and that can be utilized. And this is a case where the couplings which are there as a result of this can be utilized to do a controlled phase flip in this kind of a 2 qubit operation. So, many different operations of these kinds are possible, and this is very simple in terms of operation, because this mimics the classic case of the theory that we were discussing at the very beginning of this course, where we were it's in some sense it's the textbook criteria definition of many of these gates implications on single qubits and 2 qubits which were initially introduced. This particular aspect of using ion traps gets it so close to that, and therefore, ion traps were one of the natural early sources and advantages that have been happening with this case. And most of the time the readout is done by shining the light of an appropriate frequency where the ion fluorescence. So, many cases the readout is essentially done by shining a light of an appropriate frequency that reads out the property of the system by making the ion to fluoresce according to whether the electron is in the lower state or in the lowest energy state or not. The C naught gate application, for instance, required about 50 microseconds to perform, and the coherence times, as we were discussing, can be 20 times as long. And so, these kinds of systems are very effective in terms of application of the gates, because the time scale issues are not much of a problem. So, here is an example case of implementation of the Deutsch-Joshua algorithm using trapped ions, and which shows the suitability of ion traps in quantum information processing. A relatively simple algorithm, and it uses, in this particular case, using only one trapped ion. The two problems which are looked at is essentially the more common DJ algorithm, or the Deutsch-Joshua problem, where the individual concerned is going to use constant or balanced function, and the other individual is supposed to determine which kind the individual has used. And so, basically it is the job of the reader to be able to find out what the function is being used by the person concerned. The other problem is to use the coin toss problem, where it is the Deutsch problem, where the coin toss is whether it is a fair or a forged coin is being utilized, has to be determined by the user. So, there are therefore 4 different types of coins that we are looking at it here. Essentially, we have these as defined earlier in terms of DJ algorithms and Deutsch algorithms, that we are essentially looking for constant functions versus balanced functions, and there are 2 cases for each of these, which makes this different kinds of coins we are talking about. What we have is, in one case we are using the third line is essentially finding out the addition modulo 2 of the 2 which we are looking at. We are applying the application of these individual functions, and then we are looking at their result accordingly. So, the implementation aspect therefore is essentially solving this particular diagram, in which we have the input. So, these are A and W which we are inputting, and accordingly we are looking at their different aspects as we go along, and before we finally make the measure. And there are these unitary transform gate that is being applied, which does the addition modulo, and that is what is being used. So, the Hadamard gates are the ones which are originally being utilized to get to the initial condition, which is then is going to have the unitary being applied to it to create the addition modulo, which would be of these different kinds as we look at it. And so, we basically can do both these algorithms in with the help of just a single ion in this case, because we can have the different modes of the ion coupled to each other and get this done. So, here is a example which has been taken in case of the calcium ion inside the linear trap, where the states of the motional degrees of freedom are being relabeled as the states of the state. So, this motional degree is essentially the condition of the ion within the trap. So, roughly this is the one which is like this simple harmonic oscillator condition of this trapped ion, whereas the so that is the one which is to be set up in terms of the degrees of freedom, and the Doppler sideband cooling is the way where which creates the which prepares the ground state. Typically, whenever a laser interacts with these kinds of a trapped ion, depending on whether the leading edge is doing the job or the trailing edge does the job, which is what is meant by the Doppler sideband part. The leading edge creates heating, whereas the trailing edge essentially does the cooling, and that is how the ion is cooled. So, the idea is to make this motion minimally minimal as it gets cooled, and this is due to the interaction where the momentum of the particle of the ion is getting decelerated because of this interaction with the applied laser field. So, the two qubits which are involved in this case, as I mentioned, is the two level atom in itself, which is the well, in this particular case is the atom slash ion, because we are looking at calcium ion with one electron in the excited outermost shell. So, it is the in some sense it is a two level system with the lowest possible excitation, the lowest energy outside the core shell is just going to have one electron, which is then corresponds to the ground state, and then the next level up is its excited state. So, in spectroscopic term symbols we have the S state and the D state, which we are looking at in this particular case for the calcium ion, and it is then getting coupled to the harmonic motion of the trap, as we just discussed, which is the one where we have these two states being coupled. So, the electronic quantum state of the ion as well as the photon number of the axial vibrational mode are the ones which gets coupled because of this particular principle, and they can they are the ones which are being put together as our qubit system, which can be swapped. These states which we generate as a result of this coupled states can be swapped by the help of a pulse sequence, as I was discussing, and this is the reason of the use of a laser or RF. It depends on which particular condition we are talking about. Mostly it is the laser which is used for the addressability, which is what is going to address these joint energy levels and make these states be swapped as a result of the interaction with the laser pulse. The manipulation of the trapped ion therefore results in these. So, we have these resonant pulses which perform the single qubit rotations, whereas the detuned pulses perform the two qubit rotations. Thus the so we have these detuned pulses which would do the two qubit rotations, because the detuned pulses will essentially have the Doppler effect of sort of cooling the system or heating up the system. So, that creates a situation of having the two qubits, whereas the resonant pulses are going to either take it from one particular F level to the other particular one particular spin condition to the other particular coupled spin condition. This manipulation is therefore achievable by a sequence of pulses, which is what is utilized for getting these states. The main sources of error in these kinds of experiments have been that the phases introduced by light shifts of the lasers may not be appropriate, and the system may leave the computational subspace, because if the trapping fails for some reason or the other, then for a particular ion, let us say, then it would leave the computational subspace. So, these are the two different cases, but in most cases these are pretty controllable. So, is once in a while these are the error sources that can come. So, typically this is how the time evolution kind of shows up in one of the typical experiments, where it was first depicted years ago, and that was shown that these different qubits that are being prepared by these conditions for this particular case of the calcium ion can be spin and the vibrational mode which are being excited and looked at as a part of this. So, basically the d5 by 2 states is being looked at by this particular technique. Now, when as we discussed in the last case, it is only a single qubit system, I mean single ion system, which has been subjected in effect, which has been subjected to a coupling of two different parameters or two different quantum conditions under the condition that we are doing the experiment. If we want to have lot more ions being put together in this kind of a schematic, scaling up has many different issues to worry about. As the number of ions go up, the ion string gets heavier and the gates get slower, because now we are talking about phonon interactions of a larger mass, and so the interactions become slower, and therefore the effectiveness of the gates which are going to do these changes will become slower. And there are much more motional modes to be taken care of, which means that there is a greater noise condition. So that is basically saying that we have difficulty in cooling the system, because we have lot more states which are already getting rise to as a result of the size of the system. So, optical multiplexing always helps in these cases. So, for example, here is an example where if the system is put in such an array where these independent trapped system can be individually addressed by using fiber optically coupled lasers. So, then they will have better capability in terms of addressing them. So, that is one option. The other aspect which has been also looked at is to use the cavity mode of the system. So, this is more to do with the cavity coupling of the system with the ions that we are now talking about, and these can be connected by using cavity modes and the qubits. Now, we have not really studied much about the cavity QED aspects also. That is another way of looking at quantum computing. So, once we again revisit the cavity QED kind of problem, we will perhaps have a space where we can see how the coupled condition of the ion trap with the cavity modes can also be effective in terms of producing or enhancing or scaling up the problem. So, everywhere what we are essentially coming to understand is that it is not just one particular way of looking at the problem that we are interested in. Whatever more ways we can couple the system and have more different approaches that we have used, if we can couple them, then they are going to give us better answers, and therefore we have often utilized the principle of the already existing optical approaches, let us say, in addition to the ion trap. And similarly, we have been using the other approaches of teleportation and other things which are often available very effectively in the optical approaches into these different modes. So, here is some work which has been done very heavily by these groups. In fact, the Bose-Einstein group, which received the Nobel Prize in Nis Boulder, does a lot of work in this particular trapped atomic and ionic qubit systems. They in fact were one of the first to demonstrate many of the events that we have also discussed here. There is a University of Wisconsin group, University of Maryland, and and so there are many groups around the world which are looking at it. And this particular work, where ytterbium ions, 7 of them were coupled together and utilized, is a very important aspect of trapped condition. And so, here is an experimental setup condition which was utilized while this particular experimental approach was done. So, these are the 7 qubits, and they are separated by about 2 micrometers from themselves. So, this in this case, for example, this ytterbium qubit can be, these photons can be collected in about 100 microseconds every time they are in one particular state or the other. Is hyperfine ground state, for example, of these particular state, particular ion can have an excited electronic state which can then fluoresce back, and so this is a bright state coupling. So, we have these 2 different spin conditions which are then being satisfied. So, the spin conditions are provided by the hyperfine ground states, which via excitation to the electronic excited state can be made to go one way versus the other. So, that is one approach of showing how the ytterbium qubit works. The other thing is that once the higher hyperfine state is populated, then that is not coupled to any of the excited state. So, that is sort of known as the dark state, because in the previous case where we looked at the bright state, there was a coupling. So, the light could essentially the excitation would essentially bring back the light, and that coupling could be seen, whereas in this particular dark state there are no photons to be collected as a result of that. So, most of the probability is the fact that there is no decoupling or like decoherence, or like there is no state which is going to result, because this is not a coupled state. So, excitation whenever only if this particular spin state is populated, then it is the bright state, whereas the excited the other rotation state is populated, then it is the dark state. So, this corresponds to the dark state, and this corresponds to the bright state. So, so these hyperfine ground states are the ones which are sort of utilized for getting into these states, which have been put together in terms of the mapping which are shown here. So, so for example, a combination of these states from one particular spin hyperfine spin condition, which is of lower energy, is being utilized with utilized with respect to the electronic excited states to produce a coupling between these two different states, and these can be mapped by using this kind of approaches, as has been shown in this particular diagram. And if you want to learn more about it, you may want to look up the original paper by Craig and Solar in 1995, where they have discussed this entire process in detail. For this particular class, we are not going to go into these kinds of details, because that take a lot more effort than what we are actually trying to show in terms of implementation aspect. Here we would like to actually just suffice to point out that the laser beam is essentially looking at a motional condition of the trapped ion in the system, which is then being excited by the laser at different positions, and by looking at these laser interactions, we are able to do the interactions which are going to make them the internal states of these ions entangled in one way or the other. So, this is basically the principle as to how the experiments work. Once we accept the fact that the states are going to be coupled by using the laser, which is going to bring them come closer. So, so here for example, the coupling between these states, which I just showed with the laser again, which I will again show you, is possible due to these states getting coupled, and that is the exact thing which is being shown in this cartoon, where initial laser essentially puts some of this study here, and then there is this other coupling which is done by the other state, and then finally the third one puts it all together such that the internal states of these ions get entangled. This is in similar to the initial IJ states of the ions that I had shown in the last lecture, where at the very beginning I was discussing as to how the ions of a particular set can be coupled in these kinds of scenario. So, this is actually a practical application of that initial opening few slides, where I had shown how to address different ion sets and then have them coupled. So, ion traps have gone from being just very complicated objects, being under vacuum and other kind of difficult conditions, to states which can be addressed in terms of chips, which when put under appropriate conditions, they can be again addressed and brought back to the similar conditions. So, here are some ion trap chips which are being showed. These are the studies from different groups, where they have essentially put together how they have done this entire process in solid state conditions, where these channels and these conditions were these injection points are the ones where these trapped ions are being placed and they are traversed and they are addressed, and this is typically how these different systems are. And as you can see that they are very small and miniaturized, 100 micron gaps in one direction. This is the whole device is about, in this case for example in Sandia, is about 2.2 millimeters. In Lucent also, as you can see, these are all the technologies that they have developed over the years, and they are very well addressed, can be utilized in many different cases. Currently, the ion trap quantum computers that we are looking at are up to about 10 ions that we are have managed to see. In our particular presentation here in this class, we have shown experimental setups with about 7 ions in place. However, for actual useful applications, say for example factorization of a 200 digit number, there would be requirement of about 3500 qubits, and if you would like to implement that with error correction, there should be about 100,000 qubits. So, it requires a lot more scaling up than where the current condition is for the ion trap case, although it has been an excellent startup point for demonstrating some of the very classic or the textbook style concept principles for quantum computing. It needs to be scaled up, and so there have been a lot of applications as or attempts. So, one of the cases in terms of scaling up, for example, these are solutions that we found in many of the literature cases. This has been related to coupling, for example, to optical schemes, which has been attempted by Max Planck, Garching, where they used the calcium, as we discussed in this particular case. The case of the Max Planck Institute of Quantum Optics from Garching, they used as calcium ion as one of their ion trapped condition, and they were able to address the calcium ions by using the optical light sources, and that was the one where the resolution was limited by how far or how far away these ions could be put together. And so, the resolution there is about lambda over 10, which is quite a good resolution. The Unitzberg, for example, with the same ion has been addressing this by using laser detuning, and so that they have been utilizing the cooling principle, and that particular one has resulted in over lambda over 100 resolution. So, the resolution is much better when it has been utilized in terms of the Doppler shift condition, because that is the one which is using the advantage of cooling the system. So, and it essentially is looking at differential coupling to the motional sidebands of these kinds of motion. So, in terms of scaling up, as we mentioned before, it would perhaps be interesting to see a CCD coupled device, for instance, where the charge coupled device kind of a condition, where these segmented electrodes which are necessary for manipulating and motion of these ions are being put together in such a way so that they sort of look like a coupled condition. And in these kinds of charge coupled conditions, which is the work of this particular groups, where they claim that they could essentially use the idea of a CCD into making into a quantum CCD by using the segmented electrodes to bring the ion trapped ions into this condition where they would be creating the accumulator, and they would be keeping the rest of the ions waiting for action as memory once you have encoded them and kept them. And this particular works for ion traps, because as we have discussed, ion traps have a very long coherence times that they can be kept as, and their interactions and their time scales that we have been discussing of their decays are very, very long. And so, this particular approach of design condition, where we are setting up states like this, and they are being cooled or interacted by using lasers or RF or other ways of addressing them are being done in this accumulator or these other places where they can be made to work with. And so, this is a design condition which can be provided, which has been provided by these groups, and if you are interested you can look more into these papers to realize or understand a little bit more on this area. The other interesting way of scaling up the problem has also been using physical multiplexing aspects, where the ions are being transported between traps, so that they can have a larger number of traps which can be put together, and trapped ions which can be put together, and they can then be subjected to the different RF or laser conditions to achieve the kind of information processing that you would be liking to do that, or put in information and manipulating them in terms of data registers. So, that is another approach which has been used, where there are two different cases. One is by using interferometric approach, and the other is by separating the ions by using RF electrodes. So, in either case generally the end result is the fact that you are applying lasers to kind of see how they are going to interact, and they can be made to work. If the separation is made too large, for example, here the separating electrode has been made too wide, then it will not be possible to get the results effectively. And so, these are the kinds of work which have gone into these kinds of experiments to show what is the good condition, what is the bad condition. So, in case of interferometric cases, it has been shown with say like about 96.6% of success as to how this goes, or like transport versus the spin echo is one of the conditions which are used for seeing that the decoherence is minimized, and that is with 96% contrast ratio, which means that the coherence is maintained in terms of the transfer. And so, it is important to realize that these are the processes that has been utilized over the years to see if this concept of multiplexing the ion traps and their conditions can be improved. So, this is sort of how it looks like when you are looking at these physical multiplexing objects. They can be utilizing gold traps, silicon traps, and solid state devices, alumina, silicon, and this is how they have been made to go forward. There have been also efforts in making single electron quantum dots which can act like these devices, where the traps into a trapped condition, and this is the work which has been done by a group in Duke University in order to say that they can actually generate single electron quantum dot conditions, and that can also work almost as these kinds of ion traps and trapped ion conditions. But this is again one of the other cases where a different object is being mimicked to be applying to these kinds of applications of quantum information processing and coupling of the different concepts. So, but it is important to point out that different aspects of applications have been put together to make the progress. More work has happened in terms of utilizing the say host atom in a different kind of a lattice, and where the host atom essentially acts like an ion which is sort of trapped under these conditions. So, these are like solid state conditions where these are achieved. The qubit is then stored in say for example, in this case the phosphorus spin, nuclear spin inside the silicon lattice. So, this is sort of like the condensed phase version of the ion trap, where you are still individually addressing these ions or the atoms that we are talking about, but in a different format, and they can then be addressed by using different electrodes which are then be put together to be placed in different ways. So, voltages and resistors. So, these are different ways of addressing these particular variants of the very original idea of using ion traps, but it is not exactly the same way that we have been starting on the idea of ion trap. So, there have also been concepts which arise from this very basic principle of ion traps to go into superconducting currents, where the quantized flux qubit states of superconducting states have been utilized, and once again it is again a deviation from the same principle, but again it is utilizing the atomic modes and atomic conditions, and therefore, it is somehow related to how these quantum information processing started off in the ion traps. All of this have been summarized in one of these reviews which came out some years back in Nature, where they were discussing about how the qubits at that point of time have been looked at as catching the bus, catching the quantum bus kind of an idea, where they were able to transport and talk about charge qubit states, quantized charge qubit states based on these principles. And since they all have ionic behaviors, so they sort of are connected to the original concept of the ion traps. However, let me also point out that this is not exactly the way how the original ion trap principles evolved, as I have essentially showed in the beginning of the in the rest of the presentations here. Another useful solid state implementation of this area has been the principle of utilizing doped impurities in glass. For instance, this has been looking at a glass which has been doped with impurities which are fluorescent, and these fluorescence of these arrays of single impurities in diamond in the glassy structure has been utilized for this kind of cases, where the nitrogen plus vacancy impurity in diamond is the one which has been put forward as another idea of utilizing it. Most of these invoke the principle of ion traps or address it to sort of explain the way how they are going forward about it, but generally speaking, the original idea of ion trap is the one which essentially uses very high very different conditions and sort of the principle of cold atoms and things like that, which brings us to the principle of the original ion traps. So, if we look at it in this context of various aspects related to ion traps in quantum computing, this is what we have in principle, where the idea of the individual atoms and photons doing the job is where we have concentrated and discussed over the last few weeks, where we have shown that the ion traps or the atoms in optical field, we have not quite discussed the cavity QED part, but we have alluded to here and there, where it essentially shows that these can be worked on, and they can be also looked at in the present context in terms of these lattice structures, either because the ions are getting trapped or presented in this kind of a fashion where each of them are addressable in this form, or in the solid state form where they are being put together in one place or the other and they are being addressed in this particular ways. There have been other difficult principles which we have not yet addressed, but we showed some indications where these principles have been extended to, and we are what the claim is that they seem to scale better than these working condition cases. We also looked at another working case, which is the NMR case. In this case, NMR and photons by themselves. So, we will put them under the working conditions, whereas these other scaling condition ones are the ones which are being proposed and looked at more in recent years, because they are seem to stem towards a direction where they would perhaps scale better. And so, in the next few weeks that we have left, we will perhaps go a little bit more into these newer concepts of the work that has been going on in terms of implementation of quantum computing. We might actually spend a little bit of time later just to give you one of the other historic principles which has shown that quantum computing works in terms of the cavity QED, but generally we will be spending more time on principles where scalability issues seem to have been of some sort, which we are going to address in the future courses, future part of the discussions. Before I close in this particular week, I would like to point out that although presently the picture of quantum computer and information processing and the way how things are looking not quite as what we expect, and it also looks to be something of the extreme future. This is a cutting from a newspaper which came out in exactly when the first computer, the ENIAC, turned 50. So February 12, 1996 was the day, was when this newspaper came out, because 50 years before, on the same day, the ENIAC was first put to action, and although the electronics people said that there were too many vacuum tubes and it would never run, the mathematics people said there were no problems complex enough that the computers were needed. That was the thing at that time where the ENIAC team had to work on to get it to work, and this one fully operational was filled by a 30 by 50 foot room, in terms of the scale as to how this looked like, and the current day power of this particular machine is worse than a present calculator that you have in your hand. And yet this was the beginning of the concept of the computer that as we know today. And so if in 50 years computers have gone through a huge revolution as to what we know of today, there is a lot of hope still that these different implementation principles, although they are far from being what we expect or want them to be, would in the future someday become one of the major horsepowers of computing for us, which as we are discussing is quantum computing. With that, thank you very much. We will see you next week.